because I don't go through and turn off comments. I really need to. All right, so let's do some comparisons really quick. There's actually several symbols for actual capacitors, and you should be aware of them. This is another potential symbol for a capacitor. Generally one, oh, you guys can't see that. Generally one that has the curved line is considered an electrolytic capacitor. They will often follow that with a plus or a minus to indicate it's an electrolytic capacitor. We will be using electrolytic capacitors in here. The important thing about an electrolytic capacitor is it's designed in such a way so that the same plate is always the positive plate and the other plate will always be the negative plate. It's because of the substrate they use and the dielectric they use that they have to be connected in that way. When you go to get an electrolytic capacitor, you'll know you'll have one because one of the lead wires will be longer than the other. And the lead wire is the positive side. So when we break this into actual circuits and we have to actually do some construction, be aware of that. Be looking for electrolytic capacitors. Let's make some other comparisons here because this class didn't get to do electronics last year, did we? We had just started circuits. Yeah, I thought we had finished circuits, but I don't remember. It was a long time ago. I know it wasn't on the AP exam. So, and I don't know how far Mosser got either. All right, because we should have been nearly done with circuits, but he sometimes goes in a different order than I. Okay. So these are different symbols for batteries. This is a single cell battery or a multi-cell battery. The small end represents the anode and the long end represents the cathode, the positive and negative side of the battery. You recognize it's important, but understand that no matter what, batteries provide a standard potential difference. And in general, we use ideal batteries in our circuits and in our circuit diagrams and in our work. But we will have to know the distinction between real batteries and ideal batteries. Real batteries have an internal resistance, which limits their current output. Ideal batteries do not. They can produce infinite current. They have no internal resistance. And just because we're making this a bit of our discussion, you know, a resistor, which is a current device, squiggly line. There's multiple ways to draw this. So a variable resistor looks something like that, because generally variable resistors can have 3 leads, but some of them only have 2 leads. So a 2-lead variable resistor will probably look like this. When I say leads, these are points of connection. There are other symbols we will be using this year as well, like things go like they're supposed to. We will have inductors. We didn't get to inductors last year, but this year I hope to. A switch. We won't do, get to these, but we might do a couple of extra projects just for fun. This is a diode. There's a variety of different kinds of diodes out there. So the symbol for a light emitting diode is similar to this. Zener diodes are similar to this. A diode allows current only to pass in one direction. That's what a diode is. So it acts like an electronic switch in that it can only allow current in one direction. There's also, and we might use these a little bit, but it would be just for fun because they're not actually on the exam. There's no arrow there. But we might do some transistor work. And there's a variety of different kinds of transistors. I bought a bunch of equipment for us to build simple calculators last year, and we weren't able to use it. So we might use them this year. These are all the different circuit diagrams that you're probably going to need for the exam. I don't think there'll be any more than this. Yeah. Inductor. Yeah. Unlike a capacitor, an inductor stores energy in a magnetic field, while a capacitor stores energy in an electric field. So inductors are current devices, just like resistors, they are current devices. They only operate if there's a current in the circuit. Capacitors are voltage devices. That shouldn't be too far stretched for you to understand at least at this point, because there has to be an electric field there. So a capacitor, just by its design, can't pass current. I'm going to say that again because you have to have an understanding of this right at the beginning. A capacitor is a voltage device, not a current device, meaning its operation requires a potential difference and operates when there is a potential difference. A capacitor can't pass current because by definition, it's an open switch, meaning it is not a completed circuit. Now, this part's going to go a little bit against your conversations with electronics from last year, where there is no current flow for a circuit that has an open portion to it, meaning circuits have to have a connection from the positive side of the battery to the negative side of the battery. That's not exactly true. It was true enough for us last year, but in real physics and in real electronics, a circuit with a capacitor has to obey the rules in a slightly different way than they were explained to you last year. So let's consider a simple charging circuit, since that's really all we're going to talk about for the beginning of our discussions, our simple charging circuits. In this circuit, we have no resistors at all, just a capacitor, a switch, and a battery. The battery provides a voltage source, and the capacitor provides a sink for charge. Now, we would have said in the past that there is no possible flow of current in the circuit because it's an open circuit. There's no, even when I throw the switch and connect the switch, there's actually no connection between the positive side of the battery and the negative side of the battery because the capacitor doesn't allow current to flow. But the capacitor is a reservoir of charge. Again, it's like a bucket and it stores charge. So what actually happens is, although current doesn't flow everywhere in the circuit, current will flow from one side of the capacitor to the other side of the capacitor. So other things in the circuit will experience the flow of charged particles as charge is separated from one side of the capacitor to the other. Meaning over time, charge will begin to develop on the plates of the capacitor. There will be an equal amount of positive charge on one plate and negative charge on the other plate. During the time that the capacitor is charging, called the rise time, I'll say that again, called the rise time, there will be a current in the circuit. Now, generally, the rise time is influenced by the size of the capacitor. You can imagine that the bigger the capacitor is, the longer it would take for that capacitor to fill with charge, just like a bucket. But other things that influence the rise time is how much resistance there is to the flow of electricity in our circuit. Now, this circuit has no obvious resistor, but there are wires here. The wires will provide some kind of resistance, but they will help determine how long it takes for the capacitor to charge. We tend to believe that a capacitor is fully charged when its electric potential matches the potential across its leads. Being very diplomatic in that statement, so I'll say it again. We tend to say that a capacitor is fully charged when the electric potential across the plates matches the applied electric potential across the leads. The reason I'm being diplomatic is because you can have multiple capacitors in a circuit, and therefore they will not necessarily get the entire electric potential of the battery. You know from last year's discussion in physics that resistors can divide up the electric potential. So can capacitors. But we believe that when the capacitor is fully charged, this ratio will exist. Or more importantly, the charge on the capacitor will be a product of the capacitance times the potential. Or better yet, do you remember how we used Ohm's law last year? V equals IR. This is the version of Ohm's law for a capacitor. We will use this in the same manner in which we used Ohm's law last year. So when we used Ohm's law last year, one of the things that we did is we were consistently applying it in circumstances where there was series and parallel. We were using that to kind of figure out how the system divided up current. Do you remember that from last year? The series and parallel circuits? You guys who did this last year know what I'm talking about. In capacitor circuits, we don't have current flow in the traditional sense. We have a current flow that occurs in the very beginning to get the system charged. If you have multiple capacitors, though, the amount of charge they receive will be dependent on how their circuit divides up the electric potentials that are applied to the individual capacitors. So like we did last year, trying to figure out how much current flow and power dissipation there was, in capacitor circuits, we'll be trying to figure out the amount of charge and energy. So for a capacitor circuit, our job is to find out the individual charge and individual energy storage of each capacitor in the circuit. Now, one of the more interesting things about capacitors is once charged, a capacitor will remain charged indefinitely. Meaning once you have separated the charge and charged up your capacitor and it becomes positive Q on one plate and negative Q on the other, once that has occurred, you can open the switch back up. And the capacitor will remain charged indefinitely to be used some other time. In fact, you can separate the capacitor from the circuit, put it in a box, and store it as energy for a later use. There are quite a few applications of this. In fact, almost all switching houses and electrical grids have some kind of capacitor bank located somewhere to deal with fallout interruptions in power. You can imagine the number of times you guys have lost power here in Florida. You should probably compare that to the number of times you should have lost power and didn't, because a safety system was in place to continue to provide you power even though there was no more being produced or the lines had been down on the way to your place. Capacitor bank houses like this are set up in lots of places to provide power in situations where power might go out. Now, in Florida, generally, when we lose power, if it's only going to be for a couple of hours, we don't worry too much about people, their livelihood. But in places like up north, you go to like Alaska, where they can be in freezing temperatures, then you cannot interrupt power there without lives being lost because people will freeze to death. So in places like that, they have capacitor bank houses specifically designed to continually provide power in situations where the power goes out. Now, they don't use batteries because batteries have some limitations that capacitors don't. But I do also want to point out something important, that although ideal capacitors will store this energy indefinitely, real capacitors do not. Real capacitors will leak their charge to the surrounding atmosphere. Even in a vacuum, electrons will just kind of evaporate away and go someplace else. So real capacitors will slowly leak their charge. And we use that phrase to describe it, that they will slowly leak their charge. All right. So that is the capacitor as we see it in a circuit. We're going to come back to that discussion. But now what we have to do is a little bit more concrete. I would like to be able to take the next few minutes and describe how do you build a capacitor? And then how do you figure out what its capacitance is? That's what we're going to talk about specifically today. This conversation is a little bit challenging, but when we are done, you should be left with 3 pieces of information, each one of them as important as the next. You're going to have the 3 basic constructions of a capacitor. There are 3 different kinds of capacitors. There's the parallel plate capacitor. I told you guys this yesterday. There's the cylindrical capacitor, and then there's the spherical capacitor. We only actually build 2 of those. We don't build spherical capacitors. They would make, when you see one, you'll understand why they make absolutely no sense. We often accidentally have spherical capacitors, and they're dangerous because anything that's metal can become a spherical capacitor on its own. But we do make cylindrical capacitors, and we make parallel plate capacitors. And the most common type of capacitor that you'll see is the parallel plate capacitor, which we'll talk about first. To understand a parallel plate capacitor, you have to remember the infinite sheet of charge, because that's really where the parallel plate capacitor comes from. So the parallel plate capacitor has 2 infinite sheets. Now, I know what you're saying. There are no infinite sheets, and you'd be right. There are no infinite sheets. So the parallel plate capacitor, what we're going to talk about, is going to fudge the numbers. We're going to basically fudge what we call edge effects and assume that edge effects don't exist. Meaning we're going to have 2 plates that are very, very big compared to their separation distance, which allows us to assume that when charged, there is a uniform electric field everywhere between the plates. This uniform electric field is going to neglect the fact that at the edge of the plates, we have electric field that leaks out and is non-uniform. We're going to ignore that part. We're going to assume that that's very small compared to the overall electric field that the plates have. So we'll just call this part of the tolerance. Now, in order to determine the capacitance of your electronic device, you have to be able to figure out how much charge is related to the electric potential. That's what you have to do. So we're going to determine the capacitance of our systems by first seeing what the charge of our capacitor looks like compared to the electric field. That's step 1. Determine the charge of your device compared to the electric field. This is usually going to be done by using Gauss's law. Usually. Second, determine the electric potential generated from that electric field. So we're going to develop an expression for the charge in terms of the field and an expression for the electric potential in terms of the field. That's what we're going to do. That's how you determine capacitance. There's a little more that's going to go on with this. But for right now, I'm going to just show you the basics, and then we'll get into the weeds a bit later, okay? So we're going to start with Gauss's law applied to this arrangement. So I'm going to begin by considering a Gaussian surface, something that would, in this example, be able to tell us what the electric field is between the plates. I'm going to be careful to put my Gaussian surface so that part of that surface is between the plates and part of that surface is inside the conductor. I'm also going to try and make it so that my Gaussian surface is right at the edges of my parallel plates. I want to only talk about the electric field inside the capacitor. So that's the Gaussian surface I'm going to use. Now you have to imagine that this is three-dimensional. So my plates actually extend out or into the board some, and that this surface that I'm using is a box with a top, 4 sides, and a bottom. Is your imagination strong enough to do that? Because you're going to ask questions in a minute. I want to make sure that we all are thinking about the same three-dimensional box. So I'm good to go on? Okay. So we're going to do step 1 first. We're going to use Gauss's law to determine the electric field and the charge in terms of that field. Now, this is actually super ridiculous, and I'm going super, super slow. But when you see what the answer is, you're just going to go, so. I've drawn this in such a way that you'll notice all of the charge that's on the top plate is inside my Gaussian surface. It has to be. I have a conductor. The charge on the conducting plate has to be on the inside of that surface. So all of the charge has to reside here on the inside of this surface. It's being attracted to all the negatives that are on the bottom surface. So since our conductor has some kind of thickness, the inside's positive and the top part is negative, and that's going to be the opposite for the bottom plate. Fair enough? Any question about that? So I'm drawing my top surface so that it's inside the conductor. And my side surfaces are going to be perfectly perpendicular to the plates, so that when I start thinking about the flux, I can consider what the electric field must be like for all 6 sides of my box. So I'll break those into top, sides, and bottom. We are going to assume that there are no actual edge effects, that the amount of flux through the sides is so small as to be immeasurable, or at least really, really small. So basically, we're going to calculate the capacitance and not include any extra capacity that we get from the electric field that leaks out the sides. That would just tend to increase what the actual capacitance is, because we'll have a little electric field that we're not adding into this. So the electric field will actually be a little bit bigger than what we're calculating, and we're just going to assume that our capacitance is slightly bigger than what we actually calculate. And that's going to be okay. This is how it's done. So I'm going to take my my flux and have flux. Oops, I don't need a little loop. Flux for the top, flux for the sides, and flux for the bottom. Bottom. There we go. The electric field inside the top is 0. There is no flux in the top. The dot product means that there's no electric flux leaking out of the sides. So the sides produce no electric flux, which leaves just the bottom, where the electric flux can be written as E times A, where A represents the area of the top plate. Good? Yes, sir. Speak up, please. It's the top plate. Because we are using a symmetrical sized box, but I think that there can be the assumption that the top plate and bottom plate have the same area. And there is something to your question that perhaps I should definitely explain. Capacitance that we're calculating here will only include the parts of the electrical plates that overlap each other, and will not include portions of the plates that don't overlap. So if you have if you have two plates and you don't put them together and they are not overlapping, only the parts that overlap create capacitance, because our calculation is based on that. Now, there might be more capacity there than we know about, but our calculation is only dealing with the part that overlaps. None of that matters. Okay, you have to understand, when I say that the top plate and the bottom plate are very close together compared to the size of the plate, I'm not screwing around. Real capacitors use basically an oxidation process to put a single layer of atoms on one plate and then bond that to the bottom plate. So they are very big compared to their separation distance, since they are separated by just a couple of atoms. So you follow that idea there? So when we talk about the fact that the plates are very big compared to their separation distance, I am not even exaggerating a small amount. We're talking about two plates that are really close together. Okay? So if I slap on an epsilon naught, we have the charge in terms of the electric field and the area of the top plate. Now, I will remind you that we did have an expression for the electric field inside or near a infinite plate of charge. And if you'll recall, it was sigma over what? Do you remember?
2 epsilon.
Thank you. The 2 epsilon came from the fact that the electric field was on both sides of the plate. For a capacitor, we could write this as Q over 2 epsilon A, where Q over A is our charge density. The reason why there's no 2 isn't just because we were careful to put our Gaussian surface here. The reason why there's not a 2 in our answer is because the electric field outside the capacitor is 0. If you think about it for a moment, you'll understand why. One reason why is because we're dealing with a conductor on top, not a sheet of charge. We're dealing with a sheet that has a negative side and a positive side, so the net charge is 0, even though we have separated charge on the capacitor plate. But also, the top plate creates an electric field in this direction. The bottom plate also creates a field in this direction. You'll notice I'm extending it on purpose, right? Because the contribution to that electric field outside the plates will cancel out to give us no electric field outside the plates due to the separation of charge. They don't extend outside of the plates because of the layer of negatives that have to be here. Yeah. So we're going to set this aside for a minute. This is the charge in terms of the electric field. And I'm going to put it right here. I don't care. You wrote it in your notes, right? Do you need to see in the bottom right? That's too bad. Alex didn't write it down. I wonder what Alex was doing when he should have been writing it down. He was raising his hand? He didn't raise his hand, and I'm sorry, he didn't ask a question though. Do you want to ask a question now? Then why am I pausing? All right, ready to go on? All right, step 1 was to find the charge in terms of the electric field. Step 2, find the electric potential in terms of the electric field, which means now, we don't need a Gaussian surface for this, but I can't easily erase it. But we are going to calculate the electric potential between the plates by integrating from the negative plate to the positive plate, a distance d between the plates. This should get us the electric potential. And this result is stupid easy. And you should know why. Because we chose, and I specifically chose, a parallel plate capacitor because the electric field is a constant, which allows me to calculate the electric potential really, really easily because the electric field doesn't change as I go from the bottom plate to the top plate. So if I say the bottom plate is location 0 and the top plate is located at distance d away, there. So I hate for you to not see I wrote d there. Then I'm basically integrating from here to here. But with the electric field a constant, this just becomes E times d minus 0. Because the integration of ds with respect to 1 has an antiderivative of just s, which then goes from 0 to d. So that my electric potential in terms of the electric field is just E times d. Any question about that? All right, step 1 was find the charge on the plates in terms of the electric field. Step 2 was to find the electric potential in terms of the electric field. Step 3 is just to calculate the capacitance. And calculating the capacitance means just to use the definition of capacitance to state that capacitance is equal to Q over V, which is epsilon naught E times A over E times D, or epsilon naught A over D, the capacitance of a parallel plate capacitor. When you are done and you have calculated the capacitance, you'll be left with 3 important features every time. First, there'll be some reference to the space between the plates and what it's filled with. That's the permittivity constant. That's why epsilon naught is here. Second, there'll be a reference to how much overlap there is between the sheets. What is the area upon which the charge is spread out? And then there'll be a reference to how far apart the sheets are from each other. Capacitance gives you something that is clearly a size for your device, a physical size for how big it has to be. The first thing I want you to notice that capacitance is completely based on how big the object is. If I want to maximize capacitance, I have to do so by maximizing the surface area of the sheets. If I want to maximize capacitance, I want to get those sheets as close together as possible. The physical size of the device will be part of the answer for capacitance. If you guys remember resistance from last year, you had something similar. Resistors were based on their physical size. Cross-sectional area and length determined the resistance of a device. Its physical size. So one of the things about capacitors is that we're limited to how big we can make them because of their physical size. They take up space. The energy takes up space in our devices. The only thing that we can possibly do is manipulate what we know about the space between them, finding materials that might make them more hospitable for electric fields. So in general, we have limits to how big we can make capacitors in terms of their area and their separation distance. We can only get them so close. We can only make the plates so big. We want our phones nice and small, stuff like that. So what we tend to do is manipulate the space. We don't use a vacuum. We put something between the plates that enhances the electric field. And we call that a dielectric. A dielectric is a material that has the capacity to change the permittivity of space. It's called a dielectric. And what we have found is that almost every single material on the planet increases the size of the electric field, because most materials have some form of polarization within them. So if you're careful with the material that you choose, you can increase the size of the electric field in the space by just putting the right kind of material between the plates. We measure dielectrics in terms of multiples of epsilon naught. So we use something called a dielectric constant, K, to determine the dielectric of a material. And we say that the dielectric of a material is equal to K times the dielectric constant. It's actually not K, it's lowercase kappa, which looks like a capital K, but is as tall as a lowercase letter. That's lowercase kappa. So anyways, we call that the dielectric constant. And almost all materials have a dielectric constant greater than 1. They're usually some multiple of epsilon naught. Some of them huge, 100, 1500 times epsilon naught. So there are a lot of really high potent materials that can really ramp up the size of the electric field between the plates of a capacitor. So we will augment our definition of capacitance to include the dielectric constant. And problems are going to play with the dielectric constant a lot. We need to be prepared for that. So what we have here is the physicalness of a parallel plate capacitor, how you would build a capacitor. Do not get this confused with the definition of capacitance. They are different. This is how you make one. This is how it's used. I never worried about how I made a resistor when I was dealing with resistor circuits. I worried about how they performed in the circuit. Similarly, if I'm worried about how a capacitor is going to perform, I'm going to use this law, the definition of capacitance. If I'm worried about how to make one, I'm going to use this law. And that's an important distinction. The difference is we can do things to capacitors we couldn't do to resistors, which is why we will use these all the time together. For example, we can charge up a capacitor and then try and pull its plates apart and see how that affects the amount of energy stored. We can take a capacitor and slide a dielectric into it or try to slide a dielectric out of it and see how that changes or how our capacitor performs. These are incredibly common problems on the AP exam. So unlike resistors, where once you put one in a circuit, it stays the same. It's a resistor. Capacitors, you can screw with them while they're in the circuit and while they're charged. And the important thing is knowing what's changing about a capacitor when you mess with it. What physical parts of the capacitor change. So we are going to constantly be asking, does the charge stay constant on the capacitor when you make that change? Or does the potential stay constant on the capacitor when you make that change? All right, so questions about what we've done so far? Does it seem totally easy? It's not. Tomorrow we're going to do the line of infinite charge, the cylindrical capacitor. And we won't deal with the spherical capacitor for a couple of days because we're going to do the lab instead. All right, guys. Have an excellent day. Any questions at home? All right. Be looking on mastering. Your next homework assignment is getting ready to drop because it's time. So have a good day, guys.
If we were like you said, increasing the separation distance, and we just
If you were doing what?
increase D, could you just set that equal like that equation to Q over D and then solve for how the charge changes?
Depends on what you're connected to. So like if you have your capacitor connected to a power source and you start pulling the plates apart, then the electric potential stays the same. But think about it for just a minute. If we have, say we have the capacitor and it's connected to a battery, and you try to, spread the plates apart, okay? Then think about it for a moment. If it's connected to this, then this is going to stay the same the whole time. So as you pull the plates apart, how does that change the capacitance? Right, so C gets smaller. So C goes down, V stays the same, charge leaves the capacitor and goes back into the battery. See what I'm saying? That's how it, but if I disconnected it from the power source, so it's not connected to the electric potential, charge has nowhere to go. So in this circumstance, the electric potential can't stay the same. The capacitance goes down. So Q stays the same, capacitance goes down, the electric potential increases. You see what I'm saying?
Yeah. So you're just trying to find the relationship.
Yeah. And those are good questions on the exam. They do that kind of stuff all the time. You're the best. That's the entire lab worth of aluminum foil. Can you do me one favor? Put your name on it?
Yeah.
Thank you. Now we'll do the lab. Did I say we're going to do the lab tomorrow or Thursday? Thursday. That's what I thought.
Yeah, we're doing the other shape.
Right. That's what I wanted to do. I wanted to do that on Thursday so we do the other shape tomorrow because the other shape's a little harder. Thank you very much.